Okay, hello everyone to our Data Science and Data Engineering Club meeting for this week. I first wanted to start our updates where we have a flyer now on paper. I'm gonna pass it around so you all can inspect it. I got a new media design student to design it, so we have an actual artist instead of one of us trying to scribble something on a page. So I hope everyone likes it. You should be seeing them around Calisano, at least maybe around the greater campus. Okay, so our biggest update. Let's see. How do you? I don't know how to use your computer, Suja. No. Okay. Okay. Here. Updates. We're going to have a guest speaker, the one and only, our Lord Savior, Travis Cassell. First, he's going to talk about his research, and then that's going to lead into a hackathon or like a data fest, because we're giving you multiple days. We don't want you to stay up for 24 hours programming. So we're just going to give you a week to deal with the data set. I feel like that's more reasonable to do. So he's going to come in, talk about his company, and then he's going to give us a proprietary data set from his actual business. So this is actual real business, real world data. And then he's going to have us analyze it, and we'll have you guys share your results. So just start thinking about that now, maybe make some teams. I think it's going to be a really interesting data set, and it's going to be a whole lot of fun. So today, we're scheduled to do statistics for data science, and that's really it. So without further ado, I'll let Sujan take over.
Thanks, Lee. Okay, so let me go with that. Okay, thanks for joining us today, everyone. So today's lecture is called Do I Even Need Statistics? So I'd like to start off the things with a picture, actually. Let's see. So yeah, Meg is saying, you guys always act like you are better than me. So you can see. What? Can I do what?
You're not sharing your screen.
I am sharing, right? No?
There you go.
Okay. Yeah. So yeah, kind of like a lot of people think like, okay, I don't need statistics because I'm going to do machine learning, data science, or artificial intelligence. And I don't really blame them, because these three words have become the buzzword in the recent year. But as data scientist, the real data scientist, you can see that the reality is something totally different. So this is what reality actually looks like. So we have got three big cornerstones of data science here. The business aspect, that is the most important aspect, arguably. You got to earn money, right? So yeah, applying the techniques that are present to do business. And then we have their computer science, and on the right side, we have mathematics and statistics. Now let's look at the different intersections in this Venn diagram. So when we have business and computer science, it's just traditional software development. On the other hand, if we see the intersection between business and math and statistics, is traditional data science, traditional data analysis. Well, this is sort of thing that we used to do in the past century. Now, down below, we have computer science and math and stat, and the intersection there, you can refer to as theoretical machine learning research. Now, at the intersection of everything, here we have our beloved data science. So you can see math and statistics are very important cornerstones in the building, right? So yeah, and in this lecture, I'll try to convince you guys that yeah, statistics plays a very huge role in this world of data science. Now, a couple of things here. You don't need to understand everything in this lecture. What I do want you to do is that once you learn the concepts in the future, just come back to this notebook and try to connect try to build the connections, because that will be very helpful. So let's start the things with what is statistics? Well, okay, how many of you guys have taken a statistics course before? 1, 2. Okay. Yeah, probably 50 to 40%, right? So in a broader sense, what statistics really is the set of scientific methods that deals with data collection, data presentation, data analysis, and most importantly, gaining insights from the data, that is the interpretation of the data. Now, the world of statistics can broadly be divided into two parts, the descriptive statistics and inferential statistics. Now, in descriptive statistics, we try to summarize the data. We can find some properties of the data, or we can do some visualization. But on the inferential statistics, we might want to run some models on that to get something insightful from the data. So yeah, as data scientists, we mostly focus on this inferential statistics, but yeah, we do need descriptive statistics in order to present the data to someone. And as we saw in the data visualization lecture, that yeah, so we kind of focus on, we mostly focus on this, but yeah, the descriptive part is also important sometimes. Okay, now coming back to the data part. Okay, so as you know, we produce quintillions bytes of data every single day, and not every data is of same kind, right? So in statistics, we divide data into two broad categories. One is qualitative, the other one is quantitative. Now, from the from the name, you can imagine qualitative data represents some quality of the things that we study. On the other hand, quantitative data tries to quantify some feature or something like that. And again, we can subcategorize these two things, and we have nominal, ordinal, discrete, and continuous. And no matter what kind of data that we generate every single day, they will fall under one of these categories. Now, you might imagine, okay, what about video data, audio data, and things like that? Well, we can convert it into those data into one of these things. So let me show you some examples of these kind of data. So nominal data. Well, so these are the qualitative data where we cannot associate any intuitive ranking to them. For example, hair color, like black, blonde, red. There is no inherent ranking, right? But in the ordinal data, we can assign an order based on our world knowledge. So here, economic status, poor, middle class, rich, we can easily rank them. On the other hand, in the qualitative part, we have discrete and continuous. Well, these are very simple to understand. Discrete data, everything is discrete, like number of students in the class. You can't have 5.2 students in a class. And for the continuous part, is just the rational numbers, like temperature, for example. Now, you might ask, okay, why are we learning this? How will that be important in my data science journey? Well, the thing is, based on the type of data, you have to encode your feature, because machine learning models, computer models in general, are very dumb. They can't understand like humans. They only understand numbers, right? So here are the thumb rules. These are not some written rules somewhere that you have to go with this method, but yeah, people generally use this kind of things. So for nominal features where there is no inherent order possible, we have to go for one-hot encoding. And don't worry about one-hot encoding right now. If you don't know it, I'll come to it. On the second point, we have ordinal features. Now, if you have that, you can either go with one-hot encoding, or you can use something called as label encoding. I'll also come to that. Now, for the discrete and continuous features, almost always we use real numbers for them, but sometimes if the number of unique values in your discrete feature is too less, if you have, I don't know, how many children's a couple have, it cannot, it is mostly restricted, right? It cannot be too large, it really be 100. So we can somehow convert them into one of the qualitative data and encode like that. So yeah, let's see how you can do one-hot encoding using pandas.
You're gonna drop the notebook for them?
Sorry?
You're gonna give them this notebook?
Yeah, I'll give them. I will give you the notebook. So don't worry about running the code right now. So yeah, we have a fake data set where one column is hair color, the other one is economic status. And in hair color, we have some examples: black, blonde, red. On the economic status, we have rich, middle class, poor. So this is the data frame. Now, my favorite way of doing one-hot encoding is using the pandas method get dummies. So the way to use this is very simple. You just need to call the function and pass the columns parameter, and there you have to input the column that you want to one-hot encode. So after one-hot encoding, the data will look like that. So for those who don't know what one-hot encoding is, try to see that in the first row, the hair color was black. And here, the function has generated 3 new columns: hair color black, hair color blonde, hair color red. And in the first row, as black was the case, so this is 1 and others are 0. And similar, by following the similar logic, we have generated the one-hot encoded vector for every feature. Now, intuitively, what we are doing is we are converting the categorical feature into a binary feature, like it's either 0 or 1. Okay, any questions so far? We're good? Okay. Just stop me if you have any doubt and question, I'll answer. Okay, next comes the label encoding. So remember, I told you like we can use label encoding if we can assign an intuitive ranking to the features. You have a question? Oh, okay. I thought you raised your hand, sorry. Okay, so I know a lot of people recommend using the scikit-learn for that, but my personal recommendation would be to just use the dictionary. The reason I'm suggesting this is if you use scikit-learn label encoder, it won't know the natural ordering that you are trying to get there. So it's better to do it manually. Just create a dictionary, and the keys are the features in the column, and the values are the ranking that you think are appropriate.
The natural ordering meaning like it can assign 1 to 4 as well, like randomly.
Yeah, if you do the scikit-learn, I think it assigns randomly. But in this way, you're making sure, okay, there is a order that I don't want to break. Now, to apply this in a particular column, there's obviously a lot of ways to do that, but the most pandas way, I think, is just use the apply method. And this piece of weird code, for those who don't know, it's called a Lambda function. Like this is nothing fancy there. It's just it is a function, one-liner function, and you have x as your input, and your output is the corresponding value from the dictionary. So if we run this, we will get this. See here, economic status has been label encoded for us. Okay. Now let's come to arguably one of the most important things in statistics is the idea of population versus sample. So what is population? Well, population is a very abstract idea. It is the space of all possible. Yeah, go ahead. Okay. Okay, so population is a very abstract idea, and it is the space of all possible data points that are interesting to us. Now, in real world, almost like nowhere at any point of time you will figure out the population, because it keeps changing and it's too huge to incorporate everything in the population. So in statistics, what we do, we take a sample from the population and we compute something on the sample and try to infer something about the population. Now, what are these two somethings? Well, suppose we want to know how the mean of ages of like all 7th grade students. Now, the actual mean, the actual population mean is called population parameter. But if we randomly select 100 7th standard students and compute their mean, it's called sample statistic. So remember, anything that we compute on the sample is called sample statistic, not statistics, statistic. And anything that we want to know about the whole population is called population parameter. So almost always we don't know the population parameter, and our goal is to use the sample to infer the population parameter. Now, in data science, this population is the wild, is the actual data space of everything, right? Like, suppose we are working on a classification problem where we want to classify cats and dogs. So every possible image of cat and dog will belong to this population. But obviously, we don't have access to that. So we do model training on this small set and hope that our model will work on the whole population. No.
That's how like political polls work. They don't just go around asking every
Yeah.
single person who they're gonna vote for. They take a sample of the population, ask them, and then hopefully it's representative.
Yeah, exactly. So that's the philosophy behind surveying. And with the good enough, okay, so two important things in the survey thing. You have to pick your survey, the data points, the persons who are actually taking the survey randomly. You cannot have any bias in them. Now, there are some shortcomings of the survey. As you can see, in the whole population, we have some diamonds, but we don't have them in the sample. Reason? Because they are too few. So obviously, we're going to miss out on some data points. So yeah, but in general, this is the way to go because we never have access to the whole population. Okay, moving on. Okay, now comes the measures of central tendency. Well, central tendency just means I want to check if my data is centered around some point. Now, the most easy way to check that is to compute something called as mean, which I know that if every one of you know. So see, okay, so here are some notations that I have to specify. When there is a smaller case letter, it refers to our sample. And when there is a capital case, it refers to the actual population. And usually I'll refer the population parameters in Greek alphabets and sample statistic in English alphabets. So this is a very simple formula for mean. You just sum all of your data points and just take and divide by the number of data points you have. So in sample, we divide by the sample size, and in population, we divide by n. Now, this line the last line might be new to some of you. So what it's saying is, if we do the sampling process infinite number of times, and we take the average sample mean, we will get the actual population mean. So this is called expectation. So that's the explanation of what an expectation is. And this is good because this property is satisfied, and we can actually mathematically show that. So the sample mean, we call it as an unbiased estimator of the population mean. Because if we sample 100 times and take the mean, we will virtually we will know the population mean, which is our target most of the times. Now, obviously, okay, so we can easily implement the mean using that code. I'm not gonna explain the code because it's very simple. We had a class about NumPy. So yeah, we just use that. Now, obviously, mean is not the only way to measure central tendency. We also have median. Well, median is to find median, what we do, we sort the data and we pick the middlemost value. Now, obviously, there's a corner case if the number of samples is odd and the number of samples is even. So yeah, this is how we do it. So if it is odd, we can have the middlemost number. But if it's even, there's no middlemost. There are two middle elements. We just take the mean of them. And the way to do it in NumPy is this. Okay, now coming to the mode. So what is mode? Is the most frequent value. Simple enough. And yeah, I have again taken a sample array. Now, there are obviously a lot of ways to find mode from your data. I like to do the counter method from collections package. So why? Because sometimes what happens is you don't just want to find the most common element, you do want to find like top 10 most common elements. So if I just do here from 1 to 2, it will give me 2 numbers. And the first one is the actual element, and the second number is like how many of the elements are present in the array. Okay, any questions so far? Okay, now I'm going to ask you a question. Which one to use? Anybody, any idea? Like if you have a data set, which one you should go with? Exactly, it depends on the distribution. Now, how it depends on the distribution? Like this, suppose you have these 2 distributions. You can see that in the first distribution, okay, by the way, can you read that? The green one is mean and the blue one is the median. So if the distribution looks like this, we call it a skewed distribution. So like most of the data the are on the left hand side, but there might be very high values here. So it kind of looks like this. So in this case, the median is actually less than the mean. So we say that large values here are shifting the mean towards them. And the exact opposite things happen here. Because there are there are few numbers which are very, very low. They are dragging the mean to the left. But if we have a very symmetric distribution where eventually there's no difference between the mean and median, so yeah, this thing also can happen. So in this kind of case, what we do is if it is completely symmetric, we can use either mean or median. But if we have something like that, we should use median, because as I mentioned, the mean is not the true center because because the extreme values are dragging the mean towards them. Now, why this is useful to us? Obviously, if we want to represent our data, it will be useful. But even if we want to impute our data, okay, does anybody know what an imputation is? Data imputation? Okay, so data, yeah. No, data augmentation, I guess that you are talking about. So what data imputation is, suppose you have a column that describes the grades of 7th graders, okay, in a final exam. But some of the students were absent in that thing, or the person who was noting down their results did some error. So there are some gaps in my column. So how to fill the gaps if we don't want to throw away the data? Obviously, the first line of defense is to just throw the data away. We don't want to use that row. But in some cases, this is not possible because we have less data. So the way to do the imputation is we can fill the missing values. Now, the most common way to do that, if it's a numerical feature, we just take the mean of the entire column and put them in the blanks. But if we know that the distribution is somehow skewed, then you might want to go with median imputation instead. Or take another example where the data is categorical, where the data is qualitative. So you can't take mean or median. You have to go with the mode. So any questions so far? Okay, going good. How am I doing on the time?
Pretty good. Yeah, half an hour.
Good. Okay, now we have measures of dispersion. Well, so dispersion is what we call the spread of the data, like how much the data is spread along the number line, or 2D number line, or ND number line, or whatever you might call it. So the simplest and most used method to measure the dispersion is called variance. And see here, the sample variance formula and the population variance formula are different. We have n-1 here, but that's just n here. Now, why is that? Like, does anyone have any idea why that might be true? Yeah. Yes, exactly. Remember when I was showing you this thing? Mu is equal to the population mean is equal to the expectation of the sample mean. So this was unbiased. But if you didn't have the -1 here, the -1 here, we couldn't be able to write this thing. So that's how, and there's a elegant proof of that. If anybody is interested, I can send you that, because I had to prove that once in my exam. So yeah, so just because we want this to happen, like we want to estimate the population variance, we always go with n-1 for the sample variance. And obviously, if we take the square root of that, we will have the standard deviation. Again, simple stuff. We can easily implement it in NumPy. Okay, now comes another measure of dispersion that is called interquartile range, or IQR. Well, so IQR is, it looks scary, but it's very simple. So to compute the IQR, what we do is we sort the data. We take the first half of the data, we compute its median, and we call it Q1. And we do the same for the larger half of the data, and we compute and we call it as Q3. Now, there's also something called as quartile deviation. This is not very useful because, as you can see, IQR, the only difference is just divided by 2. So yeah, I didn't see a lot of application of that. Like, mostly people use IQR. Now, the way to compute this is again very simple, using NumPy. Obviously, you can use packages like SciPy and things like that, but yeah, NumPy also works. So the way to do this is you need to compute the percentiles using the percentile function. So if you think about it carefully, you will like notice that this Q3 is nothing but the 75th percentile of the data. For those who don't know what percentile is how much of the data, what percentage of the data are less than a certain value. So yeah, so Q3 means 75% of the data are less than Q3. And yes, same for 25 percentile, that will give us Q1. So you just subtract them and you'll get the answer. Okay. Any questions? All good? Okay. Now comes like very important part, how to use the knowledge that we just discussed above to remove outliers. Now, what is an outlier? So outlier is something that is like very rarely happened in my data, and it might be due to some device error or some very unlikely case that we don't really want to bother our algorithm about. So we better throw the outliers away to have a more robust model. So the first line of defense against outlier removal is something called as Z-score based method. So what is that? So this is of the famous normal distribution. I'll come to it later if we have time, but for now, just imagine this is a normal distribution. This is the curve of normal distribution. And one of the fascinating things about this curve is if you add these 3 probabilities, it'll come up to about 99.7%, and you'll see that they lie between 3 standard deviations from the mean. So this is the mean, by the way, and this sigma is just 1 standard deviation. So yeah, so more than 99% of the data lie between this range. So we can actually neglect everything that comes after it or comes before it. So the way to do it is very simple. Again, I'm describing data set here, data set of temperatures. So what's the outlier here? Yeah, absolutely. So we need to get rid of that. Now, so here's the thing that, yeah, so to do the outlier removal, first we need to change our data set a bit. So we compute this thing. So this xi is the values here, and x bar is the sample mean, right? So we do this and divide by the standard deviation. So effectively, what we are doing is we are treating our distribution, our temperature distribution, as a normal distribution. Although remember, this is not the case. Like actually it is not normal distribution, but we are just assuming, okay, let's see that it would be a normal distribution. Then we are just neglecting everything that are 3 standard deviation away. And okay, one important thing, the standard deviation of this normal distribution, this is called a standard normal distribution with mean 0 and standard deviation 1. So if I compute the z-score method, okay, to do this, actually you need the SciPy API. See that 120 is more than 3 standard deviations because it's 3.1 and our standard deviation was 1. So 3 times that is more than that. So now if we just run this code, again, this is just a pandas syntactic sugar. You can just have a conditional statement here, and anything that is more than 3 will be discarded. So see, we have got rid of that. Now, I'll ask you a question, like, can you think of a scenario where this method might fail, like not very robust? Yeah. So like, remember, like, again, this was also not normal distribution, but we assumed it was normal. So yeah, you are correct. When it is like too not normal, like it's too skewed, then this method might fail, because then our assumption would be more flawed. Our assumption is flawed to begin with, but yeah, it's still like not that bad. But if it was like this, suppose if the distribution was like this, or like even more skewed, then our assumption would be very bad. So to deal with that, we use the Iqr based method, because remember, in Iqr, we don't have the mean in consideration. We use the medians. So this is more robust to skew distributions. So the idea here is we compute 2 thresholds, lower threshold and upper threshold. And this is computed as Q1 minus 1.5 times Iqr. Now, don't ask me why 1.5, why not 2? I don't know. Like people, like that's the convention. People usually use these 2 numbers. And by the way, when you look at the box plot, that's what it's saying. So here, this is our median. And here, this is our lower threshold and higher threshold. And anything that falls beyond this range, we will treat as outlier. So yeah, we compute the Q1 and Q2, okay, Q1 and Q3. And by the way, okay, can anybody tell me what Q2 is? Yes, exactly. So yeah, I didn't write it anywhere here. So yeah, we compute that, and again, some pandas, and we have removed our outlier. Okay. Any questions so far? Okay, yeah. Like I don't get it. So z-scores will be, yeah, z-scores can be from negative infinity to positive infinity. And if in our example, like if the z-score is less than -3 or greater than +3, we will discard that.
So the reason it was negative is it's the z-score for that value in the table. So that's why it came, like, the only reason it's higher is the z-score for the value of 67 is -0.4. It's just a corresponding z-score value. Okay.
Yep. Okay. Now let's come to covariance and correlation. Now, try to remember when we talked about variance, it was a one-dimensional thing. Like, yeah, we have the mean somewhere here, and we can measure the variance. But what if we want to measure the spread along two different dimensions? So the problem with that is this. So here I have written the variances along horizontal axis and vertical axis. You see, this data distribution and this data distribution have exact same x variance and y variance, but they are not the same distributions, right? Because one is like something like that, other one is like that. So to incorporate this thing in our analysis, we compute something called as covariance. So the formula is pretty simple. You just multiply these two terms, like you subtract. So just to compare it with the original variance formula, in the original variance formula, it was xi minus x bar squared. But here, instead of multiplying the same thing twice, we are taking the two different dimensions. And we have the normalizing constant, like normalizing thing in -1. Now, we also have something called as correlation coefficient, or better known as Pearson correlation coefficient. Now, the formula is the same covariance here, normalized by the product of their standard deviations. Now, why would you want to use correlation over covariance? Because this covariance is susceptible to the scale of the features. If you have one feature ranging from 0 to 1, like 100,000, another feature ranging from 0 to 1, the first one will have a bigger impact. So just we are normalizing this by their standard deviation. So the effect of larger numbers are getting neutralized. Okay, now why would a data scientist want to use correlation coefficient? Well, the simple answer is to see if there exists a relationship between one feature and the other feature, or some feature and the target. As you will study more like data science algorithms, some algorithms has an assumption that the feature should be independent. Like I think naive Bayes algorithm does that. So yeah, in those kind of scenarios, you want to know that the features you are using for your model are actually like independent of each other. Now, the way to see it is very simple. I think we also saw this in our data visualization class, is the heat map. So yeah, this is our fake data. And we just compute, and pandas has this beautiful function, .cor, and it will show you the correlation coefficients. Yeah, so by seeing that, you can see that, okay, our target y is heavily correlated with x1 and x2, but x1 and x2 are also very correlated. So if we had to use naive Bayes, we might want to use only one of them. Okay, now this is very interesting part. This was correlation is not causation. If two things are correlated, it doesn't always mean that they are like one is causing the other. So there's a famous website. I highly recommend you to go to this website and find some correlations that might shock you. They're not real correlations. They are just randomly, like it happened because of the randomness. So yeah, you see like total revenue generated by arcades correlates with computer science doctorates awarded in the United States. That's like, yeah, these two things are completely different. It just happened to be the case they are correlated. Okay, now why this might happen? So the first reason can be, if you look hard enough, you can find pattern in randomness. So pi is an irrational number. It's also a transcendental number. If you look at the digits, you can probably find your phone number or your birth date. I'm pretty sure you can find your birth date like in like 100 million digits of pi or so. I didn't find my number, but I did found another person's number. So yeah, you can try. So yeah, if you look hard enough in randomness, you can find correlation. You can find patterns. Now, the second reason might be is two variables can correlate because of a third unknown factor that is not known to you. So to give you an example, it's a very silly example. So there was a survey which found that students from age 1 to 6, if we take the data and we do some analysis, we find that their reading ability is correlated with their weight. Does anyone have any idea why this might be the case? So some scientists took age 1 to age 6 students and did the study. Any idea why?
Assuming that the lower ages were lighter.
Yeah, exactly. But at one go, you might think, okay, there might be like some who are heavy might not, like who are heavy, they are reading actually more than the light ones, but that's not the case. There's a completely different factor behind that. So whenever you want to make some inference from the correlation result, be aware that it's not that one is caused by the other. There might be a third factor that is unknown to you at the moment. And yeah, another thing, like a low correlation score doesn't always mean that there doesn't exist a correlation. It's simply could happen because there exists a non-linear correlation. Because in my plots here, you see, like we can only measure linear correlation with this method. We can't say that one is like exponentially correlated with other, or like square root term, something like that. Okay. How much time do you have?
15 minutes.
Okay, we are good. Okay, now let's come to the normal distribution. Some myths and facts. So this is the same plot that I showed you before. So this is the scary formula. I don't think you need to remember that, but just remember that there are two very important parameters that define our normal distribution. That is mu, that is called the mean, and the standard deviation. So some important things about it. It's symmetric about the mean. And you see, moderate values are the most likely thing. So it's not skewed to one end, like this is the moderate value, right? These values will be very low value and this will be high value. And see, the height is maximum at the middle. So what it tells us is the moderate values are the most likely values. And very high values and very low values are equally rare. It's not that higher values are slightly less rare than the lower values. Now, why this is so useful? Well, in one word answer would be because of the central limit theorem, but I do want to give you some more insight in that. So the thing is, like, when you throw a dart at something, if you are like focusing on a particular point, what happens is you'll see some darts are going to that like left to, and some darts are going to the right. It's not that everything is like slightly more darts are going to the right. So in general, if you are focusing on something and you are trying to like pinpoint there, and there is some randomness, most likely the randomness will not be biased towards a certain end. It most likely it will be like unbiased, like it will be same in both the direction. So in nature also, it's not like that. If you take the height of females, it's not like that the highest values are too likely, like it's always at the median. So in nature also, it's like, so the reason normal distribution is very useful is because by just using two parameters, we can mimic something that is very natural in this universe. Like any random process you take, chances are it follows a random distribution. it is very unlikely that it will follow a skew distribution. Now, one thing I do want to make sure, like if when you take a random process in the nature, it's not always a random, it's not always a normal distribution perfectly, but it's good enough. Because we just have to estimate 2 parameters, and we can like pretty reasonably describe the process. So that's why normal distribution is so useful. Okay, now coming back to the CLT part, central limit theorem. So what it says is, regardless of the population distribution, remember the abstract part, population, we don't know about. Regardless of that, like I don't care what distribution the population follows. If you take the sample mean, like if you take the sample mean of like 1,000 samples or like 1 million samples, the mean will follow a normal distribution. So in the first example, I have a uniform distribution where every value is equally likely, and I did it for like 101 time, I guess. I sampled 101 times and plot their histogram of the means, and I found this plot, and see how closely it mimics the normal distribution. Now, it's not only true for the continuous distribution. Even if you take a discrete distribution, this is called a binomial distribution. Again, the same thing will happen. And even if you take a very skewed distribution like exponential distribution, then also you see the normal distribution pops out. So yeah, this was the gist of central limit theorem. Obviously, there are much more to that, but yeah, that was my point about like why normal distribution is so useful. Okay, now coming back to the last section, that is how to know that your model is statistically better than the previous models. So as you will be more experienced in data science, obviously you're going to train more models, but it is surprisingly hard to show that the model that you have is statistically better than the other models. So for those who will take a stat course, you will get something called as t-test, which will just is a way to say, okay, if the mean of one data point, one sample is significantly better or like significantly larger or less than the other sample. So you might think after taking the stat course, okay, I have 2 models. I will compute the K4 cross-validation matrix for both of the models, and I'll just run a t-test. But surprise, surprise, it won't give you the actual insight, because while doing the K4 cross-validation, the metrics that was generated are not independent. So that's why the standard tests are not very helpful here. So how to do it? Well, the first thing is you can just accept the fact that, okay, whatever statistical test I'm going to run, they would be biased in some nature, but still I'm going to use them because they are easy to use. The other thing that you can do is you can just compute the K4 cross-validation matrix. Well, for those who don't know what K4 cross-validation is, suppose you have a whole data sample, the training set, so-called, and you divide into some parts, like you divide into 5 parts, and you train your model on the first 4 part and test it on the last part, and you just keep moving the window. So you take the first one, leave the second, and take 3, 4, 5. So you do that. So you will have 5 matrix. So what some researchers do is they do that and take the mean and standard deviation, and they see if the confidence interval overlap. Now, what do I mean by confidence interval? I'll show you here. Another thing you can do is called as McNamara test. It is specifically useful for classification algorithms. So yeah, if you have some project where you are comparing 2 different classification models, you can check that out. They have a very beautiful explanation of McNamara test, and you'll have more links to follow from there. Okay, now to end this presentation, I have some models that was trained by us hypothetically, and these are the accuracy matrix. Now you see what do I mean by the confidence interval is this. So my model, the mean was 86.9, but my standard deviation was this. So my confidence interval would be that minus the standard deviation to my mean plus the standard deviation. Now, if you look at all the points, see that Tolu's model does not overlap with the other models, but all the other 4 are overlapping. So we cannot say that my model, Ritu's model, Lee's model, current models are better than one another. But we can definitely say that Tolu's model is better because it's the confidence interval does not overlap with any other model. So yeah, that was the thing. And I will share this notebook with you. And do you have any questions?
So in the end, what you said was, is it the concept of hypothesis?
Yeah, so
Not that alternative.
yeah, exactly that we do in t-test, but we can't do it while evaluating our models. Actually, if you go to this link, they have a very good explanation of why can't we use that. But I have seen research papers where people just report their mean and the standard deviation. So yeah, that was it.
Okay, thanks everyone for coming. This is going to be the last of like our heavy like tutorial like meetings, I would say. So now you have all the pieces to go on. If you're new here, we're gonna post the recordings of all of our meetings. So far we've done a NumPy and Pandas tutorial, we did a Matplotlib and Seaborn tutorial, and now you have a statistics tutorial. And from here, we're going to really take off. So make sure you guys know all of that, maybe go back and watch those recordings, because from now on, we're just going to go straight into, just diving into the data science. And if you have a good